Welcome to the big video where we discuss Pearson Edexcel Further Mathematics, Further Statistics 1. So I must have mathematical formulae and statistical tables, but instead of having statistical tables, I rely on calculator. Okay, so I think we can start. Question number 1. The discrete random variable x has probability distribution given here. So it's incomplete distribution law given in the table, where a and b are probabilities. Find expected value of x. So despite the fact there are so many unknown probabilities, so we can still find expected value. So I just followed the formula. It says the value of the random variable must be multiplied by the corresponding probability. And I continued this process times a, 0 times b, 1 times a, plus 3 times 0.3. So I can see that a and minus a disappear, and 0 times b also disappear. And it's 0.5 with negative sign plus 0.9, which results in 0.4. That's it. So maybe you were threatened by the fact that you don't know A, B, but we can find expected value even if you don't know A and B. So given that variance of x is 3.9, find the value of A and the value of B. Okay, so we can start by considering the basic property of any probability distribution. The sum of the probabilities sum up to 1. So 0.25 plus A plus B plus A plus 0.3 must be equal to 1. So let's combine like terms. So 2A plus B is equal to 0.45, right? So it's the first equation. Then we can use the fact variance is 3.9. So variance of x, I know is expected value of x squared minus expected value of x squared, everything squared. So what is expected value of x squared? So all the values of random variable must be squared, and then each value must be multiplied by the corresponding probability and then summed up. So minus 2 squared is 4, but I multiply by the corresponding probability, plus next value, minus 1 squared is 1, times the corresponding probability. So 0 squared is 0 times b, 1 squared is 1 times a, plus 3 squared is 9, 9 times 0.3. But it's only expected value of x squared. Then I subtract expected value of x. Here it is. We found it in part A, 0.4. It must be squared. So it's given the value is 3.9. So I have to combine like terms. Okay, let's see. It's 1 plus a, so b disappears. Oh, okay, a is the only variable here, so isn't the only unknown. I mean, so 2a is equal to, so everything must be like moved to the other side. Let me use my calculator. It's 0.36, so a is equal to 0.18 then. So which automatically means that b is equal to, so you put it here, 0.009. So here are the two values, a and b, they asked about. Okay, that's it. Next, C part. The independent random variables x1 and x2 each have the same distribution as x. Okay, we now know a is 0.18, B is 0.09. Okay. Oh, sorry. 18. So find the probability that x1 plus x2 is bigger than 3. So we have to consider all such combinations that makes x1 plus x2 bigger than, strictly bigger than 3. So let me continue here. Probability that I think it could be, so x1 is equal to, say, 1, and x2 is equal to 3. So this combination is good. Or x1 is equal to 3, x2 is equal to 1. So it's like I'm finding this combinations manually, or x1 is equal to 3, x2 is equal to 3. Is it enough? Yep, yes, it's enough. It's equal to, what is the probability for x1 to be 1? Here it is, it's 0.18. And at the same time, x2 must be equal to 3, but it happens with the probability of 0.3. Or means plus, x1 is equal to 3, 0.3, times x2 is equal to 1, it's 0.18. It's multiplication between them because these two events happen simultaneously, plus x1 equals 3, it's 0.3. And x2 is equal to 3 with the same probability of 0.3. So here I use the fact x1 and x2 are independent. So the fact that x1 is equal to 3, it doesn't affect the fact that x2 is equal to 3 because they are independent. Okay, I use my calculator. It's 0.198. That's it. That's it. Okay, so we move on. Telephone calls arrive at a call center randomly at an average rate of 1.7 per minute. It means we're dealing with poison flow of events. After the call center was closed for a week, in a random sample of 10 minutes, there were 25 calls to the call center. Okay, so carry out a suitable test to determine whether or not there is evidence that the rate of calls arriving to the at the call center has changed. Use 5% level of significance and state your hypothesis clearly. Okay, I don't think it's enough time. It's enough space to write over there. So A, part A of the problem. So we have a null hypothesis that lambda, so rate, it's 1.7. It was 1.7 per minute. It was 1.7 per minute. But during the 10 minutes period, it would be 17 per minute. Okay, let's write 17 per 10 minutes, per 10 minute period. So it's my null hypothesis. It's always must be expressed in terms of an equality. So it must be equal sign over there. So HA, alternative hypothesis, let's read it carefully. Whether or not there is an evidence that the rate of calls arriving at the call center has changed. So this phrase means it can change to the left or to the right. Means lambda is not equal to 17. So it's two-tailed test. Two-tailed test. It means. Okay, so we can carry out a suitable test by determining the p-value, right? So p-value consists of two parts. It consists of two parts. So it was 25 calls to the call center. So it means my p-value consists of two tails. It consists of two tails. Let's draw a figure to represent it. So this is the mean value of 17. But we observe something, I don't know, is it abnormal or not? We can consider, we observe 25. So this is one tail, and there will be another tail. Yep, so I can just take one tail and then multiply it by 2. Okay, let's do it. P-value is 2 times probability that x is bigger than or equal to 25, where x follows Poisson distribution with lambda equals 17. So I take my calculator. So it's 2 times 0.0406. This probability was produced by a calculator, and we have to compare it with the significance level. My significance level is 5%, so I compare this value with 5%, which is, my value is apparently bigger than 5%. So what does it mean when p-value is bigger than alpha? So p-value bigger than alpha, so means I accept null hypothesis. So the full phrase must sound like this. So with 5% significance level, I have no enough statistical evidence to reject the null hypothesis. So in other words, I accept it. But I don't want to write this full phrase because it's so long. So B part. Okay, only 1.2% of the calls to the call center last longer than 8 minutes. One day, Chang, I think it's Chang, has 70 calls. Find the probability that out of this 70 calls, Chang has more than 2 calls lasting longer than 8 minutes. Okay, I think it's all about binomial distribution. So, okay, let's say B follows a binomial distribution with n equals 70. It was 70 calls, and the probability that each call is such that it lasts more than 8 minutes is 0.012, 1.2%. So this is number of calls lasting more than 8 minutes. Yeah, so it's a good, it's a good habit to define the random variable. So I fully defined the random variable by saying its meaning, by saying what distribution it follows. Then, so we have to state the problem in mathematical language, find the probability that out of the 70 calls, more than 2 calls lasted longer than 8 minutes. So it means probability B is bigger than 2, more than 2 calls. So B, the number of calls, must be bigger than 2. So in other words, it's 1 minus probability B is less than or equal to 2. So pay attention to this. So it was a strict inequality over there, but when you use the complement principle, so it becomes less than or equal to. So because only this type of probability can be found in my calculator, I use Casio. So the result is 0.0523. So you go to the calculator, you choose Bean CDF. Yep. So and by default, it gives you the probabilities of this type when B is less than or equal to something. This is X value you put. Of course, you have to fill in the parameters N and P. So, and don't forget to subtract the probability you found from 1. Yeah, it's maybe a common mistake made by students. So let's move to the part C. So the call center records show that 95% of days have at least one call lasting longer than 30 minutes. Okay, so on Wednesday, 900 calls arrived at the call center and none of them lasted longer than 30 minutes. Use a Poisson approximation to estimate the proportion of calls arriving at the call center that last longer. Okay, so C. Okay, so we know that probability that there is at least one call, there is at least one call lasting longer than 30 minutes is 0.95. So let's P is probability that a call, one call randomly chosen, lasts longer than 30 minutes. Yeah, like this. So then let's say that N is number of calls that lasted more than 30 minutes, right? So out of 900. Yep, out of 900. And then we have to use, if we don't use any approximations, then N of course follows binomial distribution with N equals 900 and probability P, unknown. But we can replace it with an approximation that follows a Poisson distribution. So it can be approximated by Poisson distribution. Lambda is, NP, it's 900p. It's 900p. So then we are given the probability that N equals 0. It's 1 minus probability N is bigger than or equal to 1, Yep. So it was given. Yep. So the probability that at least one call, it was at least one call longer than 30 minutes. That probability was 0.95%. So probability no such calls is 1 minus 0.95. It's 500ths. It's 500ths. So I know how to approximate this probability N equals 0 with Poisson distribution. I just use the formula for the probability from Poisson distribution. It's e to the power of minus lambda, which is 900p, times lambda to the power of 0, because N equals 0, divided by 0 factorial. So it's a full formula. So, and this value is given to be 500ths. So this can be ignored because it's 1. 0 factorial is also 1. So the equation I have to solve looks like this. E to the power of minus 900p is equal to 500ths. Of course, I take logarithm of both sides. It's minus 900p equals a ln of 0.005. So I can use my calculator. Let me do it. Okay, p is equal to 0.0033. I think it's more than enough. Okay, yeah, so it was pretty, it was a puzzle to solve this part C, but we did it eventually. So let's move on. So let's go. Oh, how much space is given? Okay, so in a class experiment each day for 170 days, a child is chosen at random and spins a large cardboard coin 5 times, and the number of heads is recorded. Okay, the results are summarized in the following table. Oh, it must be chi-square test. Marcus Aurelius believes that binomial distribution with parameters 5 and 0.5 can be used to model this data, and he calculates expected frequencies to 2 decimal places as follows. Okay, and find the value of R and the value of S. Okay, so it sounds easy because the distribution is given. So I can use my calculator, but I have to produce some specific probabilities. I mean, for specific values of X. X equals 0, X equals 2. So that's why I use binomial PDF, bean PDF function of my calculator. So R is the probability that X is equal to, or B is equal to, I don't know, B or X. Let's use X is equal. So this is X is equal to 0, but I have to multiply by its expected frequency. It's not probability. Oh, it's not probability. It's expected frequency. So I have to multiply by the number of experiments or trials. It's 170. So I multiply by 170. So my calculator helps me. So it's 85 over 16 or 531 if rounded to three significant figures. Okay, it's R and S. It's probability that X equals 2 or 3. They're identical. So don't forget to use binomial PDF again, and you multiply by N, by the number of trials. It is 425 over 8 or 53.1, three significant figures. Yep, so it's calculator work, but I pointed out on the subtle moments you have to pay attention at. Okay, B, carry out a suitable test at the 5% level of significance to determine whether or not the binomial distribution is a good model for this data. You should clearly state your hypothesis, the test statistic, and the critical value used. Okay, so do I have enough space? Okay, let's try to write over here. So H0, null hypothesis. So data follows binomial distribution. So this is my null hypothesis. And of course, alternative hypothesis denies it. So it doesn't follow binomial distribution. Okay, it's my hypothesis. Then after that, it's chi-square test. So I have to find chi-squared observed value. Yep, observed value. So it can be found using the formula. Observed minus expected squared divided by expected. So I use this frequencies as observed frequencies, and this is expected frequencies. So I put them in the formula. So I can give an example. Observed frequency is 3. Here it is for the first entry in the table, minus expected is R, is 531 squared divided by expected 531. And we continue in the same manner for all the rest values. So I can see that expected frequencies they are all big numbers. Yep, because there is a condition that says that expected frequencies must be at least 5, but it's okay with it. So if computed, I used my calculator. It is 2741. So it's chi-squared value observed. And then chi-squared critical. So I have to open it. Oh my God. So this is, so in the beginning of the video, I said that there is no need in statistical tables, but it was a mistake. So chi-squared critical must be found using the tables. So let me give you some additional information. Degree of freedom. What is degree of freedom? It's 6. 6 is the number of columns in my table and minus 1. It is equal to 5. It is equal to 5. Alpha, it was given, right? So it's 5% significance level. It's a tradition for A-level questions. So 5%. Then, so I looked it up in the table. It's 11.07. So my chi-squared observed is significantly bigger, right? 27 is significantly bigger than 11.07. Chi-squared observed is bigger than critical value. So what does it mean? We reject null hypothesis. The full version of your answer sounds like at 5% significance level, we have enough statistical evidence to claim that the data does not support the null hypothesis. That is, the distribution does not follow binomial distribution. The distribution of the results of spins. It doesn't follow binomial distribution. Okay, but we usually do not write such a long conclusion. So we move to Nima. Nima believes that a better model for this data would be also binomial distribution, but with a different parameter p. Find a suitable estimate for p. So in order to make an estimation for p, we use expected value of x. So its theoretical value, look at the distribution, it's NP, so it's 5p. Theoretical value of expected value is 5p, but estimated value, it comes from the data we observed, right? So it's value of the random variable 0 times the frequency 3. Oh my god, I have to look at the table. 1 number of heads, 1 times the frequency 10, 2 times 45, 3 times 62, 4 times 38, and 5 times 12. And then I divide by the total number of observations. It was 170. So it means P is equal to, I used my calculator again, 249 divided by 425, or 0.5858. Is it enough? Okay, 82. More digits, more figures. That's it. So this is an estimate for P. So the estimation came from this two methods of finding expected value of x. One, theoretical NP formula for binomial distribution, and based on the sample data. Okay, to test her model, Nima uses this value of P to calculate expected frequencies as follows. Okay, it's a lot of work done for us, so thank you very much. The test statistic, they even gave us the test statistic, because it would take me I don't know, 5 minutes, maybe 4 minutes to put all this data. Okay, in my calculator. State giving your risen degrees of freedom. Okay, DF, degrees of freedom. So let's take a look at the expected frequency. Oh my god, expected frequencies. So this value must be combined. Yep, it must be. So 2.07 is too small. It's less than 5. So I have to combine this two columns of my table, and it's considered to be one column, second, third, fourth, fifth. So the basic number of columns in the table is 5. I have to subtract the number of parameters that are calculated, they were not given. So I calculated the value of P, right? So I used this data. No, not this data, but I used the data, like I collected to find the estimate of P. So it means I have to subtract it once. And one should be subtracted because this all data is, this all data, so they are also like connected to each other, because I know, because if I knew this, it would be easy to restore this. So there is a connection between them. So that's why I subtract one more. So it's 3. So this is due to the parameter P estimated. This is basic value of 1 that we subtract every time. So this is 3. Yep. So next, the critical value. Okay, so I appeal to the statistical table. So chi-squared critical for degree of freedom 3 and alpha equals 5%. Yeah, 5% significance level. So I looked it up. It's 781. Okay, E, with no reference to Marcus and Nima's test results, comment on the probability of the coin landing on head. Okay, with reference. Okay, with reference to the results. Oh, but we have to perform the test. So 162 is less than 781. So we accept. Right, we accept binomial n and p 5, 0.58, 58, 82. We accept this hypothesis. So with reference to Marcus and Nima's results, so Marcus' hypothesis was rejected. So we can't say that P is equal to 0.5, but we accepted Nima's hypothesis. So Nima's hypothesis says that probability P is 0.58. So the probability of the coin landing on heads, so I can say that it's bigger than 0.5, or more specifically 0.50, okay, let's say 59. With 2 significant figures around this value. So what can we say about the independence of the spins of the coin? Okay, if we accept binomial distribution, then we have to accept independence automatically, because binomial distribution implies independence. Yep, so yes, they are. Yes, they are. They are independent, because it follows from the nature of the binomial distribution. Okay, I gave reasons for my answers, but it was like oral explanations. Okay, it was interesting problem. Further statistics is very interesting. It's my most favorable exam. So let's move on. Oh, such a short question. Let's use blue ink, sorry. So number 4, there are 32 students in a class. Each student rolls a fair die repeatedly, stopping when their total number of sixes is 4. Okay. Each student records the total number of times they rolled the die. Estimate the probability that the mean number of rolls for the class is less than 27.2. Okay. Okay. Total number of sixes is 4. So it smells it's negative binomial distribution. Let's say X Okay, let's say let X is a number of trials, a number of attempts before, not before, number of attempts on having four sixes. So it means X follows binomial distribution. What are the parameters? R is a number of successes we are like waiting for. So R equals 4, and P, probability of success in each attempt, of course, is 1/6, right? Because it's a fair die. Yeah. So I know expected value of X. It's easy formula, R over P. So it's 4 times 6, I think it's 24. Yeah, it's 24. So, yep. So it's expected number of attempts. Estimate the probability that the mean number of rows is less than 27 if we know there are 32. Oh, it's central limit theorem. Oh, yeah. So that's why I have to find a variance. Variance of X. So the formula is R times 1 minus P times P squared. Yep, it's geometric distribution, but times R. Variance of geometric distribution, but times R. So it's 4 times 1 minus 1/6 is 5/6, and 1/6 squared. So I can rely on my calculator or just work mentally. 30 times 4 is 120. This is variance. And then we consider the sample, yeah, because we're talking about the mean number of rows for the class, for all 32 students. So X bar is sample mean. Let's say it's sample mean. And according to the central limit theorem, which applies here, because N 32, the sample size is big enough, and all the attempts are independent of each other. All the students' attempts are independent of each other. So according to this central limit theorem, X bar follows normal distribution with the same mean. Mean remains the same, but variance of 120 must be 32. That is sample size times less. Yep, so it's variance. So, and then estimate the probability that the mean is less than 27.2. So probability, the mean is less than 27.2. We know the distribution and all the parameters of X bar. So I have to put this information in my calculator. Yeah, I use my calculator. Thanks to Casio for inventing such a wonderful thing. As Casio, I use FX 991EX model. Cheap, reliable, and so smart. So it's 0.9508. Yep. That's it. So it's central limit theorem. And you have to recognize I said binomial. No, it's negative binomial. So sorry. Negative binomial distribution. Yeah, so the two key steps here is to recognize negative binomial distribution and the central limit theorem. Of course, you have to know a bunch of formulas: expected value of X, of negative binomial, variance, and also formulas when you apply central limit theorem. Okay, it was number 4. And we can move on to the next, oh my God, so long question. Let's use violet ink now. A machine fills cartons with juice. The amount of juice in a carton is normally distributed with mean mu, it's unknown, and standard deviation 8 milliliters. A manager wants to test whether or not, oh my God, it's tests again, The amount of juice in cartons, X milliliters, is less than 330 milliliters. The manager takes a random sample, it's N, 25 cartons of juice, and calculates the mean amount of juice X bar milliliters. Using a 5% level of significance, find the critical region of X bar for this test. Okay, so I think I can work here. So what I know, X is amount of juice, right? Amount of juice. It follows normal distribution within a known mu. But what was standard deviation? 8. So 8 squared must be written here because it's variance. Then I have to state hypothesis. Yep. So H0, my zero hypothesis is that mu is equal to 330 milliliters. Yep. Yep. So we are questioning this hypothesis. Is it 330 milliliters? Yeah, so the alternative hypothesis states that it must be less. So alternative hypothesis says that it's less than 330 milliliters. So it's one-tail test, one tail. Yep, and the sample size was 25. So X bar now, X bar. So because, yeah, we have a sample of cartons of juice. X bar, according to the, it's not a central limit theorem because it's a property of normal distribution. X bar follows normal distribution with the same like mean from the null hypothesis, 330, and its variance, which is 64, not 8. Yeah, be careful with it. Must be divided by n, by 25. Oh, that's it. So then we have to produce the critical region. Oh yeah, so critical region. So we have to reject the null hypothesis if X bar is less than some critical value, and the probability to fall into this region is significance level. What is significance level? It's 5%. It's 5%, so popular. It's 5%. So looking at this diagram, it's easier to understand what is happening. So X bar must be less than C. Yeah, this probability is given as 500. So it's an inverse normal distribution problem because, you know, area, left area is given. All the parameters of the normal distribution are given, so we can use inverse normal function of our calculator to produce the value of C. So that value of C is 320.4, maybe 4. Yeah, 4 is good. 4. So it means critical region looks like X bar is less than 327.4. If your observations are such that the mean value of them, mean of the 25 observations, fall to the left of 327.4, then you would reject the null hypothesis. It's a rejection region. But if it's bigger, then you accept null hypothesis. Okay, it's A. Then B was B. Find type 1 error for the director's test. Sorry. The director is concerned about the machine filling the cartons with more than 330 milliliters of juice as well as less than 330 milliliters of juice. The director takes a sample of 55 cartons, records the mean amount of juice, Y bar, and uses a test with critical region. Okay, it looks like this. Find probability of type 1 error for the director's test. Okay, we have to recall The definition of the type 1 error, yeah, probability of type 1 error is probability to reject null hypothesis given that null hypothesis is true. So, okay, how is it true? How is it true? So let me draw a diagram again. How is the null hypothesis, how is it true? It's true when the mu is 330. And how do we reject null hypothesis? If the sample mean falls in one of these two critical regions. Yeah, the critical region splits in two parts, the left one and the right one, because it's given. It's given in the task. 328 and 332. Am I right? Yep. So we must find the probability to reject H0. We reject H0 when we are here in the tails. So it's probability that y bar is bigger than 332 and then multiplied by 2 is due to the symmetry. So what do I know about y bar? Y bar follows normal distribution with 330 as the mean. And what is its sigma? 55. Oh, you see, and the sample size has changed. It's 55 now, but the standard deviation remains the same. So it's 64 standard deviation squared, but divided by 55 now, not 25. Be careful with it. So I use my calculator. It says 2 must be multiplied by 0.03186 at 0.06373. Yep. Yeah, this is the type 1 error. Okay, then when mu is actually 325, find type 2 error. Okay, so green, C part, actual mu is 325, no idea where it comes from, milliliters. Probability of type 2 error. Type 2 error. I know the definition. It's probability to accept null hypothesis. I know where I accept the null hypothesis. This is acceptance region. Acceptance region. And while the null hypothesis is false, I know how exactly it is false. It is false because mu is 325. So in other words, it's probability. It's probability. But by the way, they are asking for the type 2 error in the test in part A. Oh my God, I was so close to make a mistake. So it's not an acceptance region we are interested in. Let's go back. This is an acceptance region we're interested in, and this is rejection region or critical region. Rejection region, acceptance region. So C was found. It's 327.4. So probability that X bar is bigger than 327.37, given that mu is equal to 325. This is exactly how H0 is false. And sigma, what is sigma? What is sigma? It's a test in part A. This is test in part A. So here was variance. So sigma is root of this value. So it's 8 over 5. Yeah, sigma is 8 over 5. 8 over 5. So you can find this probability easily. Again, using a calculator, 0.06927. That's it. So it's crucial to know the formulas, the definitions of type 1 error and type 2 error, and then you can understand what regions to use, what mu's to use. It's so important. Okay, let's move on to the next question. So it's question number 6. Is it the last question? Oh no, we have 2 questions more. Oh my God. Okay, I see it's more space here. Maybe I'll be able to write down my solutions over here. So number 6, the discrete random variable x has probability generating function. Okay, specify the distribution of x. So it must be given in the formula sheet, the table of PGFs, probability generating functions for different for different distributions. So gx of t can be a little bit rearranged. So let's take out the square. So it's t divided by 3 minus 2t. And if I divide both sides of this fraction inside the brackets by 3, so it's 1/3 t, 1 minus 2/3 t. Yeah, so, and then when you look at the table with PGFs, so you recognize negative binomial distribution with r equals 2. So this is r, the power of the brackets, and p equals 1/3. This is the coefficient of t in the numerator. Okay, it's a negative binomial distribution. Then, so let me write down compare with PGF from the formula booklet. PT divided by 1 minus PT to the power of r. Okay, a fair die is rolled repeatedly. Describe an outcome that could be modeled by the random variable x. Oh, it's just 1 mark question. So we have already defined the name of the negative binomial distribution, so we just have to describe it. It's number of attempts until a success occurs. Success occurs 2 times. Yeah, 2 times. Probability of success is 1/3. Yep. So use calculus and probability generating function to find expected value of x and variance of x. Okay, I think it will take more space. So I know expected value of x is probability generating function, derivative of it, and derivative calculated at 1. So here is the probability generating function. So I have to differentiate it, g prime x of t. Let's rewrite it because I don't see. So t squared. Oh, let's write it this way. T divided by 3 minus 2t squared this way. And then we differentiate. Yeah, so we first differentiate the outer function of squaring. So 2 goes down. I rewrite the base. Its power now becomes 1 less, but then I multiply by the derivative of the argument using the quotient rule. It's 1 times 3 minus 2t minus t times derivative minus 2 divided by 3 minus 2t squared. Yep. I don't want to simplify it because it's pretty easy to put the value of 1. Okay, 1. So 2 times 1 times 1 plus 2, it's 3. Yeah, 3 divided by 1, 3. So it's 6. So expected value of x is 6. It's just a matter of arithmetics. I don't think you have to use your calculator because it's too long. It's a lock that 3 minus 2 times t, when t equals 1, is just 1. That's why you can ignore this. So it's pretty simpler. It's simpler to use your mental skills. You are on a further maths. It's not like grade 8 or grade 7 mathematics. You have to be able to perform such calculations in your mind. Okay, variance. Okay, variance. So to find variance, we have to find the second derivative of g at t. Okay, I think I have to simplify it. Oh my God, I have to simplify it. So the denominator is 3 minus 2t cubed. It's non-negotiable. So let's open the brackets. Oh, it's just 3, yeah, because minus 2t and plus 2t, they disappear. It's just 3. 3 times 2t is 6t. Oh, this function should be differentiated once again. So u prime v minus u rewritten u prime v minus u v prime. V prime is 3 minus 2t squared, and don't forget to multiply by the derivative of what we had inside, just by minus 2. Divided by 3 minus 2t, everything squared, power becomes 6, twice as much. So it follows that g2 primes at 1. Oh, 6 plus 6 plus 36 divided by 1. It's 42. Yeah, so variance of x, it is the second derivative at 1, and then plus the first derivative at 1 and minus first derivative at 1, everything squared. This is the formula. So it's 42 plus 6, but minus 6 squared. 12. Yeah, it's 12. It's 12. Yep. But we haven't finished yet. Yeah, it was 7 marks, but we have D part. Yeah, D part. It was C part. Okay, the discrete random variable y, a new random variable, has probability generating function. Oh, looks weird. Find exact value of probability that y equals 19. Okay, I have to recall a wonderful property of probability generating functions. If y is equal to ax plus b, then probability generating function of y of t, is equal to t to the power of b, this b, times g of x, but its argument now is t to the power of a. It's easy to be proved. I don't think you have to prove it on your exam, but then if you compare gx was t squared divided by 3 minus 2t squared, right? And gy is t to the power of, where is it? T to the power of 10 divided by 3 minus 2t cubed to the power of 2. Yeah, if you compare them, you can easily deduct that. Do you see? T to the power of a. Yep, so you replace t with t to the power of a. Its power now is 2a. And then you multiply by t to the power of b. So the power of t would increase by b. And the result is here, it's 10, right? It's 10. So this is the first equation. And then let's see what is happening at the denominator. So when you replace t with t to the power of a, this happened. T now is t cubed. So it means a is 3. So a is 3. So put it in the first equation, b is automatically 4. So it means y is 3x plus 4, b is 4. Okay, just by comparing them, just by having the formula, the property in front of your eyes, it's easy to deduct a is 3, b is 4. So then probability that y, what was the question? Y equals 19, right? Probability that y equals 19. In other words, it's probability that 3x plus 4 is equal to 19. So we can solve this for x, 5. X equals 5. What is the probability that x equals 5? So probabilities can be found from the decomposition of the probability generating functions. It's t squared over 3 minus 2t squared. That was the original form of the PGF of x. So I can rewrite it t squared like 3 minus 2t to the power of minus 2. So 3 can be taken out as a common factor from the brackets. 3 then to the power of minus 2, it's 1/9 t squared, 1 minus 2/3 t to the power of minus 2, looks like this. Then I can apply binomial expansion to this part. 1/9 of t squared remains the same. So I have to open the brackets until I get t cubed term, because then multiplied by t squared, it will give you t to the power of 5, but t to the power of 5 coefficient will be exactly probability that x equals 5. This is the nature of probability generating function. Okay, let's apply the binomial expansion. It's 1, so I can skip like the term where power of t is 1, power of t is 2, and power of t is 3. It's minus 2, minus 3, minus 4, and minus 1 and minus 2 divided by 3 factorial is 6. Then minus 2/3 of t is power 3. Yeah, so of course it continues. So I multiply these two terms. I use my calculator, to be honest. So t to the power of 5 term looks like 32, 243 t5, and so on. So as you know from the definition of the probability generating functions for discrete random variables, this is, oh my god, this is probability that x equals 5. It's probability that x equals 5 is 32 over 243. That's it. Okay, that was a good question, good problem. Let's move on. Oh my god, it's problem number 7 we have still to solve. Each time a spinner is spun, the probability that it lands on red is 0.2. Okay, it's either geometrical distribution or binomial distribution. Find the probability that the spinner lands on red for first time on the 4th spin. It's just negative binomial distribution. So if the first time on the 4th spin, then it's geometrical distribution, right? So first 3 attempts were failure attempts with probability of fail 0.8 in each. 3 attempts were fails. Then the last one, the 4th one, was success. So this is the probability. It's 0.1024. The 3rd time on the 8th spin, Oh, it's negative binomial distribution. So we consider the first 7 spins. From 7 spins, 2 must be successful. So we use binomial distribution formula, 0.2 to the power of 2, 0.8 to the power of 5. It's what happened on the 8 first spins. The last attempt must be successful. So we multiply by 0.2. I use my calculator, 0.05505. Probably I wrote too much figures, but it's okay. So exactly 4 times during 10 spins. It's again a negative binomial distribution from the first. Oh no, it's not. It's a binomial distribution. Yeah, because the number of spins is given exactly 4 times. Yeah, it's binomial distribution. C then 4 from 10 attempts, 4 must be successful with no further conditions. 0.2 to the power of 4, 0.8 to the power of 6. You can use binomial PD function. It's 0.08808. That's it. So every time you just had to recognize the corresponding distribution. So it was geometrical distribution, it was negative binomial, and this is just binomial. So each time the spinner is spun, the probability that it lands on yellow is 0.4. In a game with the spinner, a player must choose one of 2 events. R is the event that the spinner lands on red for the first time in at most 4 spins. Okay. Why is the event that the spinner lands on yellow for the 3rd time in at most 7? Okay, we can calculate the probabilities easily. Showing your calculations clearly determine which of these events has the greater probability. Okay. First one. So if we consider a specific number of spins, then it's a geometrical distribution, but it's at most 4. So we have to consider 1 spin, 2 spins, 3 spins, 4 spins. So it's easier to write it in terms of sum, right? Sum x is a number of spins. It runs from 1 to 4, and each time. So it's like we calculated in part A. So it's 0.8 to the power of x minus 1 times 0.2. Yep, so this is geometrical probability in the case when x attempts will happen. So I use my calculator, it's 0.5904. Okay, then probability of y. Lands on yellow for the 3rd time in at most 7 spins. It's negative binomial distribution. So the number of let's say it's sum again. X equals 3 to 7. Okay, and then we have to find probabilities that I don't know. Let's introduce a new random variable t. T is x. So x like spins. Like we need an x spins. So t follows negative binomial distribution with r equals 3 because 3 we wait until 3 successes happen. And p is equal to 0.2 because we are interested in yellow. Oh, it's not 0.2. It must be 0.4. Yeah, 0.4 because we're interested in yellow. And then we sum these probabilities up. Yep. So I use my calculator. If you don't know how to use sigmas, You can find each individual probability for x equals 3, 4, 5, 6, 7. It will take significantly more time, but you have no choice. So my result is 0.5801. So they're so close to each other, but this is slightly bigger. So R, probability of event R is bigger. It was hard work, but we finally finished. So I hope you found it useful for you. So bye-bye. Thank you very much for your attention.